This is my free pendulum clock. It's a hybrid of pendulum and electronics. A free pendulum does no mechanical work such as moving hands, and this one has no escapement to keep it swinging. It has one moving part, the pendulum. It's kept swinging with a magnetic drive and moves in complete silence. It gets a tiny nudge every other second. The pendulum has a small magnet attached at the bottom. As it swings past a coil below it, a 25 millisecond pulse gives it a little push. It's all controlled by a microprocessor, a Teensy 3.2. The pendulum is approximately 1 meter long to create a 2-second period. It swings past center once each second. The pendulum bob is made of copper plumbing fittings filled with lead. The pivot point at the top is a stainless steel knife edge that rocks on a stainless steel plate. This makes a high Q pendulum, meaning that without propulsion it swings for several minutes, gradually diminishing in amplitude due to air resistance. The rate of the pendulum is determined by its length. I make small adjustments to the rate of the clock by sliding an adjustment weight midway along the shaft. Sliding this weight downward, for example, increases the effective length of the pendulum, making the clock run slower. You might wonder whether the propulsion pulses from the processor control the rate of the pendulum. They don't. The pendulum is allowed to swing at its own natural rate. As the magnet passes over the coil, it induces a voltage on the coil that is detected by the processor, triggering the propulsion pulse. If you stop the pendulum, the processor would wait forever for the next swing, never triggering the pulse. In slow motion, you can see that the right-going swing triggers a blink of the LED, indicating the propulsion pulse. The shorter blink on the left-going swing is timed by the microprocessor by dividing the 2-second period in half. The Teensy 3.2 is programmed using the Arduino Integrated Development System. It keeps the time and date, advancing the clock 1 second on each swing of the pendulum. It also logs clock error and temperature inside the clock. More on that later. The roughly 1,200 lines of code have evolved, and I can load new versions on the fly without disturbing the pendulum. With commands through the USB port, I can change some key variables and read out diagnostics. The processor also drives the analog clock movement. I said there was only one moving part. I don't count the analog display because it doesn't do any of the timing. Once it's set to match the digital display, it remains synchronized. It's a common battery-operated clock movement that I've hacked so it can be driven by an 8 Hz biphase signal from the microprocessor. It's the new silent type of movement with continuous motion of the second hand. I've also tried the 1 second advancing tick-tick type of movement, but I prefer the silent type. I test new software versions on this ugly breadboard before uploading. The rapidly flashing white LEDs indicate the analog clock drive signals. I'm not a programmer, I'm an analog guy. A real programmer would likely be amused by my code. Likewise, a machinist would laugh at my plumbing fittings and improvised mechanics. I'm a hack. I've assembled this clock from odds and ends with simple tools. So how accurate is it? The microprocessor has its own clock, a 16 megahertz quartz crystal oscillator. It's very stable, and I've compensated it in software to be quite accurate. So why not make the clock using that oscillator? Well, I've done that too. but I like pendulums, so I use the oscillator as a reference to measure the pendulum. It logs the difference between the pendulum and the oscillator every 15 minutes. 40 days of data are saved in the processor that show the accuracy of the pendulum and the temperature inside the clock. I download and chart it. The error ranges in the 0.2 seconds per day range. The clock accumulates an error of around a second or two per week. I've made various improvements over the years. I initially used a thin wooden slat for the pendulum shaft. I noticed that accuracy was affected by humidity and vibration, so I tried an aluminum shaft. As calculations predicted, its accuracy was affected by temperature variations. It expands with temperature, slowing the clock. I eventually found a carbon fiber shaft, which is stiff, stable, and has near zero temperature coefficient. How could this clock be improved? If I were a machinist, I would make a more aerodynamic pendulum ball. The pivot could be improved too. Most high-quality pendulum clocks suspend the pendulum from a thin beryllium copper strip that flexes easily. This would hold the pendulum in a more consistent position. Extremely accurate pendulum clocks operate in a vacuum chamber. I wouldn't go that far. Thanks for watching.